Section 9.4, Inverse functions. So inverse functions are very important in solving equations. Um, and so suppose I have some function, some rule f, that maps x to y. Then the rule that maps each of these y's back to x will be called the inverse function. So we're going to spin this whole section trying to um, actually define these inverse functions. And so basically they're undoing what we've done. And so really inverse functions are how you actually solve equations. You keep applying inverse functions until finally you get something that's very easy to see what the solution is. So first off, let me define a surjective, sometimes called an onto function. F is said to be a surjective onto function if the range of f is the same as the codomain of f. And so, again, surjective functions are also called onto functions. So you may hear either the terminology surjective function, or you may hear us say onto function. So thus, we say that f from the set x to the set y is a surjective strange, okay, is a surjective or onto function if for every y in the set capital Y there exists an x in the set capital X such that f of x is equal to y. Okay, so I can put this down symbolically. F mapping x to y is surjective if for every x for every y in the set Y there exists an x in the set X such that f of x is equal to y. Okay, so suppose I have a mapping from x to y And the mapping looks as follows. Say I map here, here, and here. So this is the mapping F. In this case, this will be a surjective function F. Since for every y here, it came from some x. And so each y in this set capital Y was mapped from is the image of some point in the set capital X under the mapping F. However, if you have, let's say, the following rule, and let's make it look similar. And so let's say it looks basically the same. And so let's say that F maps these points in X to these points in Y. Well, notice that this point in Y is not the image of any X here. Therefore, in this case, F is not surjective. Okay. Besides having surjective functions, we also have injective functions. So an injective, sometimes called one-to-one function, F is said to be an injective one-to-one function if f of x1 equaling f of x2 implies that x1 is equal to x2 for all x1, x2 in the domain of f. So as I said above, injective functions are also called one-to-one functions. So your instructor might say one-to-one, or they may say injective, and it just depends on what we say at the particular time. They both mean the same thing. So thus, we say that f mapping the set x to the set y is an injective one-to-one function if x1, x2 in the domain of f and x1 not equaling x2, if this implies that f of x1 is not equal to f of x2. So let me give you an example pictorially, just like what we did above for the surjective and non-surjective case. So suppose I have the following. So this set X, this is the set Y. Suppose I have the following. So let's say this maps here. Let's say this maps, I don't know, here. Let's say that this maps here. And let's say that this maps here. Okay. And so let's call this rule F. And so you notice that F here is injective. It's 1-to-1 because each of these Y values came from a unique X value. And so the fact that, well, if you look here, each of these X and Y's come from a unique, the rule corresponds to, well, for every one X, there's one Y. For every one Y, it came from one of the X's. And so this rule sort of is this idea of a one-to-one correspondence. So this is an injective F, a one-to-one F. Suppose I have the following sets, X and Y, and suppose, well, I don't know, let's say this maps here, and this guy maps here. Okay? Or maybe I'll have another one. And this guy here maps over here. Okay? And we have this as some rule F. So notice that this Y is actually the image of two differing X's under this mapping F. And so in that case, this is not an injective function. And so F is not injective. Okay, just like in the case of determining when a relation was a function, we looked at the vertical line test. I have another graphical, visual sort of test to test if a curve in space represents a injective function, a one-to-one function, or not. And so we have the horizontal line test. So suppose I have a curve in the plane. Suppose that this is relative to some coordinate system. And suppose that this is the graph of a function. So suppose that this passes the vertical line test. Okay? Then, if I can find a horizontal line that intersects this curve in more than one location. So suppose that this is the graph of a function. So suppose this is the graph of y equal f of x. Then, if I can find a horizontal line that intersects the curve in more than one location, then this will not pass the horizontal line test. So this does not pass the horizontal line test. And so that says that this does not pass a horizontal line test if there exists a horizontal line that intersects this curve in at least two locations. Okay, and so if it does, then if it does not pass a horizontal line test, then this is not the graph of an injective function. It's not one-to-one. Okay. Again, let me explicitly note, I will assume that the curve passes the vertical line test. If it did not, then it would not be, it would not be the graph of a function. Okay. Now suppose we have a curve. Let's do that a little bit better. Suppose I have a curve in the plane relative to some coordinate system. And again, assume that this curve passes the horizontal line test, vertical line test. Suppose that this curve passes the vertical line test, so that this is the graph of a function. Then, if this curve intersects every horizontal line in at most one location, then we say that it passes the horizontal line test. And so this passes the horizontal line test. And so this means that every horizontal line intersects this curve in at most one location, one point. If it passes the horizontal line test, then this says that this function, f of x, is an injective function. So this is the graph of an injective one-to-one function. Lastly, a bijective function. Also called a one-to-one and on-to function. And it's also called a one-to-one correspondence. So back in grade school, they call these one-to-one correspondence. So the usual example is, say in kindergarten, they would give you cookies and they give you glasses of milk, and you pair it up for every cookie, a glass of milk. So there was a one-to-one correspondence between the cookies and the glass of milk. Okay, so F is said to be bijective if it is injective and surjective. And just like I said above, we also call bijective functions a one-to-one correspondence. Okay. And sometimes we also call them, well, one-to-one and on-to functions. And so, the idea, let me draw a little picture for you. So suppose I have some set x and some set y. And suppose I have a rule that maps each of these points to some point here. Then this is a bijective function. So each of the y's came from exactly one x. And you notice that the, oh, and I guess I could have something out here. And you notice that that the range here is the same as the codomain. Okay. If we require that the co-range is the same as the domain of my function, so there's no stragglers here, then we have the following. Well, let me give you the idea of a cardinality of a set. So the cardinality of a set is just the number of elements in a set. So the cardinality of A is just the number of elements in A, and we denote by, let's say, cardinality of A. This is just the cardinality of A. And so, if F is bijective, then you notice that the cardinality of the domain of F, and so the number of elements here is the same as the cardinality of the range of F. Okay. As a matter of fact, well, I'll say that this is the same as the cardinality of the codomain of F. Okay. And in fact, which of course, well, since it's surjective, they'll be the same. The codomain's the same as the range. So, and if F is just injective, then the cardinality of the domain of F, this is the same as the cardinality of the range of F. Okay. Let me do some examples. First, on page 376, let me do problem number 4. Okay, so in exercises 1 through 20, determine whether the function with a given graph is 1-to-1. So I have the following graph. And my function is f of x is equal to negative x squared plus 2. Well, since they've given me a graph, I can just use the horizontal line test to check if this is an injective function. And so, let me just find a line that in this case will intersect this curve in more than one location. Since I found a line that intersects this curve, a horizontal line that intersects this curve in more than one location, then I found that this curve here does not pass the horizontal line test. Since it does not pass the horizontal line test, then that says that this is not an injective function. And well, or I can use the other term. I can say that this is not a one-to-one function. And so this is not one-to-one. Now, suppose that they just gave you the function f of x equaling negative x squared plus 2. Let's try to show that it is not one-to-one using that fact. So, suppose that f of x, 1, is equal to f of x, 2. Then that says that negative x1 squared plus 2 is equal to negative x2 squared plus 2. Subtract 2 from both sides. So that says that negative x1 squared is equal to negative x2 squared. Let me bring, let's say x1 squared to the other side of my equation. So I get x1 squared minus x2 squared is 0. Well, this is a special product formula, so I can factor this as x1 minus x2 times x1 plus x2. The difference of squares is equal to the product of the sum and difference of two terms. Let's set each of these terms equal to 0 using the zero factor property. The fact that this is an integral domain. So add x2 to both sides of my equation. Subtract x2. So I get that x1 is equal to x2. And I also get that x1 is equal to negative x2. Well, I was supposed to show that if f of x1 equal f of x2, then x1 must equal x2. Well, it doesn't equal, x1 doesn't necessarily equal x2. It's equal to x2, but it could also equal negative x2. So that's not correct. So therefore, I've shown that this function is not injective. It's not a one-to-one function. Just like we showed looking at the graph using the horizontal line test. Okay, so let's do problem number 8. Suppose I have the following curve. So it looks something like this. So g of x is equal to x cubed plus 2. Well, if I look at every horizontal line, I see that this curve intersects every horizontal line in at most one location. So therefore, this curve passes the horizontal line test. And of course, this also passes the vertical line test. So did the above graph. And so since this curve passes the horizontal line test, then I have that G is injective. Okay. Let me do and so I have here that G is 1-to-1. Let me do problem number 12. So I have here the following curve. Okay. So h of x is equal to x plus 2 in absolute value. Well, notice that I can find a horizontal line, say this one, that intersects the curve in more than one location. Therefore, and of course, this curve, it passes the vertical line test. So it is the graph of a function. And, well, that's the function. And so, in this case, h, well, so this does not pass the horizontal line test. Since this does not pass the horizontal line test, then this function g is not injective. And so this function is not 1-to-1. And again, it may be instructive to actually show this algebraically to see what goes wrong. So suppose h of x1 is equal to h of x2. So the absolute value of x1 plus 2 is equal to the absolute value of x2 plus 2. And so that says that, well, x1 plus 2 is equal to x2 plus 2, or x1 plus 2 is equal to negative x2 plus 2. Okay, so let's try to solve this. Let me subtract 2 from both sides. So I get x1 is indeed equal to x2, or multiplying the negative inside, I get x1 plus 2 equals negative x2 minus 2. Subtract 2 from both sides. So I get that x1 is equal to a negative x2 minus 4. Well, that's a problem. I was supposed to have that x1 is equal to x2. Well, yes, but x1 is also equal to a negative x2 minus 4, so that's a contradiction. So that means that, no, this is not a one-to-one function. So h is not one-to-one. Okay, let me do problem number 20. And so I have the following graph of the following curve. Okay. So this is the graph of y equal g of x. Okay, and g of x is negative x squared if x is between negative 1 and 1, and it is x plus 2 if x1 is greater than 1. Okay. And so, let's do this. Well, suppose I use the following horizontal line. Well, if I use that horizontal line, I see that this intersects the curve in more than one location. So therefore, this does not pass the horizontal line test. And so G is not injective. G is not 1-to-1. Okay. Let me give you some terminology. The identity function. The identity function acts like the multiplicative identity for if I take the algebraic operation of multiplication to be the composition for my field of functions. And so the identity function is a function that maps some set x into itself and is defined by, well, for every x in the domain, it's just equal to x. And so it just maps itself to itself. So if I have any point x, then the identity maps x to itself. The inverse function. Let f map x to y, and let this be an injective function. Then the function taking y, mapping y into x is called the inverse function of f if f composed with g is the identity function and g composed with f is the identity function. In other words, G, well, maybe I'll write it this way. F of G of Y is Y for all Y in the domain of G, and G of F of X is equal to X for all X in the domain of F. Okay, so unfortunately, this is not the best sort of notation because it's confusing for students. So note the following. That F inverse, this is 1 over F. That's the multiplicative inverse. However, F this is not 1 over F. Right? F inverse, these are not the same. And so the inverse function is not the same as the multiplicative reciprocal. And so if you want the multiplicative reciprocal, you have to put like a parentheses around that. Note also, sometimes, depending on the author, for the definition, of the inverse function, some authors require that the function is both one-to-one and onto. So they only define inverse functions for bijective functions. Okay, note the following. When we did domains of functions and ranges of functions, I noted that ranges were much more difficult than domains. Well, it turns out that if we have this concept of an inverse function, it turns out that it's actually just as easy to find a range as a domain using the following fact. The domain of the inverse function is the same as the range of my original function, and the range of the inverse function is the same as the domain of the original function. So if I want to find the range of my original function, just find the domain of the inverse function. If I want to find the range of my inverse function, don't worry, just find the domain of the original function. Also note that the inverse, now this is a horrible notation. This means now when you have an inverse here, we are really bad and inconsistent, aren't we? When we have an inverse and then a parentheses and inverse, then these both are inverse functions, meaning they're not reciprocals. They're not multiplicative inverses. And so they are, yeah, I guess we are really very inconsistent. And so the inverse of the inverse function is the original function. So I guess I should note both of these power, superscripts. Oh, they're not powers. Superscripts of -1 indicate taking the inverse function. They are not, they do not indicate taking a reciprocal. Okay, let me put, where's the, here it is. Ha. Okay, let me do some examples. So I put in the charger so it doesn't die. Okay, let me do problem number 24. F of x is equal to the square root of x plus 4. G of x is equal to x squared minus 4 for x greater than or equal to 0. Okay. In exercises, (21) through 24, verify that f and g are inverse functions by showing that f composed with g of x is equal to x, and g composed with f evaluated at x is equal to x. So let's show both of those. So let's do part A. Oops, sorry about that. So let's compute f composed with g at x. And let's see if this is equal to x. So f composed with g at x is found by wherever I see an x in the formula for f, I'll replace every x by the formula given by g. So wherever I see an x here, I'm going to replace x by x squared minus 4. So this is equal to the square root of x squared minus 4 plus 4. Okay. And so, well, I can get rid of the parentheses. And well, the 4 minus 4's cancel. So this is the square root of x squared, which is just the absolute value of x. But I notice that I have this restriction here. It says that this is true for x greater than or equal to 0. Well, for x greater than or equal to 0, the absolute value of x is equal to x. So good. I've shown that f composed with g at x is indeed equal to x. But notice I needed that restriction. It turns out that this restriction is so that The curve passes the horizontal line test, so that that G here is indeed injective. Okay, let me do part B. And so, well, so this says that, so thus F composed with G at X is equal to X. And so that says that F composed with G is the identity. Good. I don't only have to have F composed with G's identity. Remember, I also have to have that G composed with F as the identity. So let's do the other part. So G composed with F at X. Let's see if this is equal to X. And so I have that G composed with F at X. So wherever I see an X in the formula for G, I'll replace it by the formula given by F. So wherever I see an X here in the formula for G, I replace X by the formula given by F. And so I have the following, that G composed with F at X is just the square root of X plus 4 squared minus 4. Well, the square gets rid of the square root. The 4's cancel. And so, yes, indeed, we have shown that G composed with F at X is equal to X. And so we've shown G composed with F at X is equal to X for all of the X's. And so G composed with F is the identity. And so therefore, well, I have that both F composed with G is the identity and G composed with F is the identity. And so that says that G is just the inverse function of F. Okay. So again, note the following, even though I've said it before in the previous note. So note that f of x is equal to the square root of x plus 4, and g of x, which we found was, well, the inverse function, was equal to x squared minus 4 for x greater than or equal to 0. However, f inverse of x, the reciprocal of x, is equal to 1 over the square root of x plus 4. So, in other words, f typo. In other words, there's a typo. In other words, f inverse is not the same as f, as the reciprocal of f. So, f superscript -1 means the inverse of f, where we're talking about composition. 2 to the -1, however, means the reciprocal of 2. And so that means 1/2. And so notice that 1 is a inverse function. It's sort of undoing what you did. And the other one is a reciprocal. However, again, bad notation. If I said f of negative 2, it doesn't matter with or without a parentheses. That's always going to equal 1 over, that's always the reciprocal of f squared. Okay. Things like f cubed just means f times f times f. You just multiply f 3 times. And this means the reciprocal. It does not mean the inverse function if you have a parentheses. So the idea is if we have some x that's mapped to y by this rule f, then the inverse function is the rule that takes y and gives us back x. And so if I had some formula for y in terms of x to find what the formula is for the inverse function, I would just interchange x's and y's. So your dependent variable becomes your independent variable. Your independent variable becomes your dependent variable. Your x becomes y. Your y becomes x. You just interchange the meaning of those, and then you get your inverse function. So let's say, problem number 26. F of x is equal to 3x plus 13. So, in exercises 25 through 42, find the inverse of the given function, state the domain and range of the inverse function. Okay, so first step here is to write, instead of f of x, write y. And so let's first write our expression in terms of x's and y's. After we've done that, then interchange x and y. So wherever I see a y, I'll replace y by x. Wherever I see an x, replace x by y. And now, solve for y. Once I've solved for y, that will give me the rule for the inverse function. So let's subtract 13 from both sides of my equation in order to isolate y on one side of my equation. And so x minus 13 is equal to 3y. Let's divide both sides of my equation by 3. And so I get that y is equal to x minus 13 over 3. So now, the last step would be, well, this is the inverse, this y here is the inverse function. So my original rule had a name of f. So the rule for the inverse function will be f superscript negative 1. So f inverse is just x minus 13 over 3. And that is the rule for the inverse function. Notice, well, let's see, what is the domain of the inverse function? Well, I'm never dividing by 0, nor am I taking square roots or any even power, even root of a negative number. Therefore, the domain is everything. So the domain of my inverse function is all real numbers. Let's look at the range of the inverse function. Well, to find the range of the inverse function, I just look at the domain of my original function. Well, the domain of this function is, well, I never take square roots, I never divide, and so therefore my domain of that would be everything. So the range of my inverse function is everything, all real numbers. Let me do problem number 32. F of x equals 4 minus x cubed. Let's replace f of x by y, interchange x and y, solve for y, and so I get that y cubed equals 4 minus x. Let me solve for y. So let me take the cube root of both sides of my equation. And well, since I'm taking cube roots, I don't have to worry about pluses or minuses or anything. And so y is equal to the cube root of 4 minus x. And so my inverse function, f inverse of x, is just the cube root of 4 minus x. The domain, well, again, I'm taking a cube root, so I'm never dividing by 0 nor taking even roots of negative numbers. So the domain of my inverse function is everything. And the range, well, the range of my original function of this original function here, well, the range is just, the domain is everything. So therefore, the range of the inverse function is all real numbers. Okay. Let me do problem number 38. And this will explain, or at least give an alternative reason why we had that strange sort of relationship on how to find these in the range for this type of rational expression. So x plus 7, this Mobius transformation. And so let me rewrite f of x as y. Next, let me interchange x and y. Next, let me multiply both sides of my equation by the least common denominator. In this case, the only denominator, negative 3y plus 5, to get rid of the fraction. And so I have a negative 3xy plus 5y equals y plus 7. And now let me try to solve for y. And so it would be nice if I did it correctly. I'm multiplying x times 5. It should have been 5x. Now let me add 3xy, subtract 7 from both sides of my equation. And so I get 5 x minus 7 is equal to y plus, oh, maybe I'll do the 3x first, is equal to 3x y plus y. And so I get that 5x minus 7 is equal to, factoring out a y, 3x plus 1y. Let me solve this equation for y. And so let me divide both sides of my equation by the constant in front of y, 3x plus 1. And so I have that y is equal to 5x minus 7 over 3x plus 1. And so the original function was f. And so let's rewrite this as f inverse is equal to 5x minus 7 over 3x plus 1. Okay, so now let's find the domain of the inverse function. So to find the domain of the inverse function, I'll set the denominator equal to 0 and solve for x. Subtract 1 from both sides of my equation. Divide both sides of my equation by 3. So x is equal to negative 1/3. Therefore, the domain of the inverse function is just equal to the set of all x's, not equal to negative 1/3. And that's the domain of my inverse function. Let's try to find the range of the inverse function. So to find the range of the inverse function, let's find the domain of the original function. And so let's find the domain of this function. And so x is equal to, so to find the domain of this, I'll just set the denominator to 0. Set 5 minus 3y equal to 0. And solve for y. Let me subtract 5 from both sides of my equation. And so negative 3y equals negative 5. Divide both sides of my equation by negative 3. And so y is equal to 5/3. And so the range of my inverse function is just a set of all y's not equal to 5/3. Okay. So if you recall, when we did the range for these type of functions, I just said, well, to find the range, all you'd have to do is look at as long as this was a linear function divided by a linear function, you just look at the leading order coefficient of the numerator, 1, leading order coefficient of the denominator, negative 3, and then you get that, well, the range would be the set of all y's not equal to their ratio, 1 divided by negative 3. And so you get the same answer. Let me do problem number 45. So let's see if I can draw this, or at least best as I can do. Probably gonna have a little trouble here, but it's a little tight. Okay, so let's see, this is negative 6, 2. So negative 6, negative 2. let's say that this is negative 3 and 5 is about here. Negative 3, positive 5. Okay, and there's a line connecting these points. And suppose I have 5, so that's probably about here. 2 is going to be about here. And so I have 5, 2. Okay, well, let's, oops, let's do this. So it says, in exercises 43 through 46, sketch a graph of the inverse function if f is the function defined by the graph. Okay, so as I said before, the way that you find the inverse function is you just interchange the meaning of x and y. And so in this case, you'll just interchange the meaning between the x and y coordinates. So this would be a 2, and that's going to be a 5. Oh, let me do it in red. So 2, 5 be about here. And then this would be a 5 and a negative 3. Be about here. About here. Okay. And then negative 2 and a new negative 6. That's going to be a little bit off, but because the negative 6 is going to be, well, close enough. Okay, let's say it's there. So this will be, oops, the point 5, negative 3, and this is the point negative 2, negative 6. Okay, and so if you notice, and hopefully I did it correctly. If I look here, that's why, because this is off. Well, see, it actually goes about like this. It should have been about here, but I can't. I have a little bit of a hard time with it because it went off the screen. But if you look at this, oh, now it doesn't look too horribly bad. Oops. Of course, I somehow changed the color. So let's say that's red. So I look here, and it should go to about there. That's not too horribly bad. So this is negative 2, negative 6. And so if I look here at the line y equal x, then if you just take this curve and reflect it upon this line, you should get the other point. Okay, you should get the other graph. Oh, so I guess it looks a little bit higher up there then. It's probably about there or something. Oops, and of course now I change the color again. Well, good enough. So this looks sort of like 2, 5. Okay, so if you look, it looks a little bit better, not that great, but if you take this curve here and reflect it about this line, you should get this curve. Okay? It would look a little better if if I didn't have such a crowded space here. Okay, let me look at problem number 48. So in 48, we have the following tabular form for a function. -2, -1, 4, 0, 2, 1, 3, 2, 11, 3, 0, 4, 5. Note that, oh, by the way, you should note that this is a bijective function. Notice that none of the x's are the same, and none of the none of the inputs are the same, and none of the outputs are the same. And so because of that, that means that this is a bijective function. And so in exercises 47 through 50, find the inverse of the function f, whose numerical tabular form is given. Well, to find the inverse function, it's actually really easy. You just copy the same table down. So there's really nothing to do. The only thing is that you just call it something different. So let's do this. -2, -1, 4, oops, that's a +4. 0, 2, 1, 3, 2, 11, 3, 0, 4, 5. So to find the inverse function, you just have to interchange x and y. So the f of x becomes x, and the x becomes the inverse function. So, well, you probably want to show it in a nicer way, but this is the answer. It's done. But if you want to maybe write it in a more orderly fashion, let's see, x is -1 is the smallest. Let's do -1 first. That's a -2. Then next is a 0, which was 3. 2 is the next guy, and then 3. 2 gave you a 0, 3 gave you a 1, and then 4 is the next guy, which gave you a -1. The next guy is a 5. The last one was an 11. Okay, and that is your function. So if you input some x, you'll get your inverse function. Okay, and that's your answer. Okay, so that really finishes off section 9.4 on inverse functions.